Our goal today is going to be to build an adaptable camera controller system that we can use to pan the camera and rotate it to focus on specific targets. You can think of this as a beginning point to any sort of camera system that you may looking to be building for perhaps a cinematic or perhaps a third-person controller or some sort of RPG or RTS system. Alright, let's get this thing running. The play button. Okay. And red cube moves over here, camera moves over there. Look at that smoothness. Backs up, look at that. Forward, very nice. Okay, and I also programmed in some rotation functionality as well. So I'm pressing the E and W key here, and it's rotating it left and right. In addition, if I rotate this, it'll still properly follow the cube. So how do you get a really smooth looking camera movement such as this? Okay, so check this out. I've got a script over here. We have 5 different properties that we can alter. Well, one of them is actually hidden. One of them is private. And we have a little bit of update code here. Overall, this shouldn't take very long at all. Just a few minutes of your time. Let's go through the basics of what's going on here. So we have a game object, a follow target. We are assigning that in the editor. If I click on my main camera, you can see here that I have this new script I made, the camera controller script. It has a follow target. We assign the object that we want to be following. We have an offset vector over here. We're going to assign some initial values to this. We've got an offset transition speed. This is going to control how quickly it will reposition the camera relative to the object. And a rotation transition speed. This is going to control how quickly the camera turns when you press Q or E. Alright, well, let's go back to visiting the code again. So, we create 5 variables. As I discussed before, this is the object that the camera is going to follow. This is the offset vector. This offset vector is basically going to reposition the camera's location relative to that object. We have an offset transition speed. This is basically going to control how fast it's going to lerp to where the camera should be. We have a rotation transition speed. As you can see, we usually use that to change the rotation here. We increase the rotation around the y-axis or decrease the rotation around the y-axis depending on which key is being pressed. Alright, here's where the magic finally happens. The first thing we want to do is we want to reposition our camera's position, the position of the camera's transform. We use a vector3.lerp, and we'll be going over how the vector3.lerp function works as well. Alright, so let's start by building a controller script from scratch again. We'll do the basics of what's necessary. Let's pop back into here, and I'm just going to remove this component. I'll stop the game mode before removing it. Any changes you make during play mode do not get kept. So, what we're going to do next is we're going to go over here and add component, and we're going to choose new script. Let's call this red roulette. Now let's name it as something a little bit more professional. Camera controller var2. I've already got the name camera controller, so I'm going to attach var2 to it. Alright, created our script. Let's open this thing up. When you open up a script for the first time in Visual Studio through Unity, you just get these basic functions. We don't actually need the start function. Let's just remove that. And let's make a location where we can store a public reference to the object we want to follow. Just as I did in the last one, we're going to write down public game object. We're telling the script that the type of object we're trying to store is a game object, and we're going to name it follow target. We're saying that the name of this game object, the name of the reference of this game object is follow target. Now, let's build a vector 3, and this vector 3 is just going to be a basic offset vector that we are going to preset first. So we'll say public vector 3. So the type of variable this is a three-dimensional vector, and we're going to say it is going to be called offset vector. Now, if you want to give it some initial value, we could say equals new vector 3, and we could just say 0, 8, 0, 8f0. And this will give an initial value of, well, let's actually attach that 8f as well. This will give it an initial value of 0, 8, 8 in the editor, which is fine, I suppose. If you are creating multiple objects, it might be nice to have some default value. Alright, over here, what we're going to want to do is we're going to want to offset the camera's transform position by the offset vector plus the follow target's transform position. Let's try it without the lerp first. It's going to look a little choppier, but it'll give you an idea of why lerps can be so powerful in game development. So let's just say transform.position equals, and we'll take the follow target's transform position, follow target, dot, we add the dot because we're going to be looking inside this thing called follow target. We're looking for the transform. We'll say transform dot position. In other words, we'll look inside the follow target, find the transform. We look inside the transform, we find the position. The position is a vector 3. We can add vector 3's together using the plus operator. And we're going to add the offset vector. Alright, let's save our changes to this, Control S or save right here, and let's revisit Unity. Alright, we're back in Unity now. Let's see. Once it's done compiling in Unity, we can take a look here and we see that we have an empty reference to a follow target on our camera. So we're going to grab this cube that I made over here, and we're going to designate it as a follow target. We'll drag it right in there. Now its follow target is cube. Now the initial value 088 should work pretty well. Let's go ahead, and in just a moment we're going to hit the run button. It could help you guys to have a copy of the game in a second tab right over here, so we can kind of move the cube around right here and see the changes on the right side. Let's go ahead and run this and see how it works. Okay, so if I move this to the right, it's just a flat, straight up movement. Very simple, very plain. Notice how the camera is remaining flat in its rotation. It's not rotating at all to face the red cube. No matter where I move it, the camera is always looking forward. That's because we aren't changing the rotation of the camera. We're just changing its relative position. Alright. That's about enough of that. Now, let's go ahead and see what we can do now to make it lerp. So we want to smooth out that movement from A to B as the camera follows the red cube in its relative position. We want to smooth that movement out. What that can do is it can kind of create times when you are moving faster and times when you're moving slower. Well, let's see. Let's pop back into our script over here. Now, I'm going to just comment this out so you can kind of compare the new result versus the old result. And I'll say transform.position equals, this time I'm going to write down vector3.lerp. Alright, I stop right here for a moment, and I'm just going to highlight something that is useful to know here. When we look at the description, it says it linearly interpolates between 2 points. To linearly interpolate between something, basically t can be a value between 0 and 1. If t is 0, then basically we're going to be saying that transform.position is going to remain at A. If t is 1, transform.position is going to become B. So basically, you can think of this as a string, right? You got one end of the string and the other end of the string. And basically, if t increases from 0 to 1, you move from one end of the string to the other end. Think of it as 0% to 100% of the position between them. Our trick here is actually we're going to self-reference. We're going to reference the transform.position as the A vector. In other words, our starting point for the string is wherever the camera is. And the ending point of the string is wherever the follow target is. Follow target dot transform dot position. And we can't forget that offset vector, because that offset vector is what's going to make sure the camera is above the follow target. Alright, lastly, this is where we use a little bit of trickery. We're going to want to make sure that the percentage remains at a certain number. We could just use 0.1f, and every frame, basically, it's going to move us 10% of the way from the transform dot position to the follow target plus offset. If you want to make this a little bit smoother, we can actually multiply this by time.delta time. And then basically what happens here is this thing becomes a velocity. So we have a change in time plus a change in velocity, or not a change in velocity, a change in time times velocity actually produces a change in displacement. So it's more like a change in percentage. This 0.1f ceases to be a standard flat 10% of the way there, and instead becomes a velocity at which we approach 100%. That's not exactly right, but that's a basic way to understand it. Later on, we can actually replace this in just a moment, but I think we should give this a test here. Let's pop back into Unity, and I'm going to go ahead and give this a little run once it's done compiling. Let's run this code, and now watch that camera. Okay, so it's 0.1f times time.delta time. It's a little bit slow. That's why we're going to want to increase that 0.1f. And we'll do that by assigning a property and making it editable in the editor. So if I move this around over here, notice that when the red cube is really far away, that it's actually moving faster. So there's a nice little distance factor over here. Basically, when your red cube is further away, the lerp happens faster, right? Because whenever your camera, for example, let's say you're making a strategy game, right? And your player goes from one end of the map to the other. You can really make a nice and smooth system for accounting for how much of a deficit there is between where the camera is and where it should be. And the speed at which it gets to where it should be can be a little smoothed out. This is an alternative way to, using the approach where you just straight up teleport the camera from one place to another, which can be a little bit more jarring. It really depends on what you're trying to produce here. This is also a really good way of creating, scrollable systems when you're making, for example, the background for your game. If you want your background in your game to be some nice looking, like if you were making a Sims game, for example, you wanted it to move from A to B, right? This just looks really nice, and it would be really nice if you just blurred out the background a little bit, just had that floating in the back. It would look nice, So this can achieve a pretty interesting effect. Well, let's work on adding in that public parameter I was telling you about. Currently, if I click on the camera, we have a follow target and offset vector. Let's add in that offset speed, transition speed we were talking about. I'm going to make a public float, and I'll call it offset transition speed, and I'm going to default it to 2.0f. In general, C#, you have to emphasize that a number is, put an F at the end if it's a float. You will otherwise receive an error message. 2.0 by itself is a double. 2.0F is a float. So, we're going to just copy this. I'll replace it right there. Save. Alright, so now we're using the offset transition speed. This will be a lot nicer. 2.0F is nice. It feels good. You'll obviously be able to change it to increase or decrease the speed yourself in the editor, but I really like 2.0F. Let's pop back in after saving, compile the script, and let's go ahead and double check that the speed is in fact 2. Alright, there we go. Looks good. Pop back into the game view, and let's go ahead and give this a run now. Alright. Look at that. Isn't that quite nice? I think so. Alright. Well, I think I've covered the basics now of what we did with the offset. Now let's go ahead and see if we can play with the camera's look rotation. In other words, what is the direction the camera is looking in? Alright. So, the first thing we're going to want to do over here is we're going to want to write down, well, let's set a, no, let's actually, we'll add the parameter to control the rotation change speed later. We're going to write down transform.rotation. Now, we talked about the position as being a three-dimensional vector, but the rotation is actually this thing called a quaternion. Quaternions are complicated, so I don't want to explain that. Instead, I'm just going to explain to you how we can manipulate the quaternion easily. If you want to look up more information about quaternions, I may do a quaternion video on quaternions in the future. I don't consider that, however, to be essential knowledge to be able to construct and edit the code we need to really make solid rotation system controls. Alright, let's go ahead now and let's see. We're going to assign the, well, let's actually do it this way instead. My camera controller over here, as you can see, I did something that looks really complicated, right? I'm using quaternion.rotate towards, who knows what that does, and quaternion.look rotation over here. What on earth is going on there? That's a little complicated, right? I'm going to break this down into chunks. So the first thing I'm going to do for you all is I'm going to construct a new vector 3. So we're going to say vector 3 difference vector equals, and what we're going to do is we're going to take the location of the follow target.transform.position, and we're going to subtract the camera's position. The camera's position can be easily accessed just by doing transform.position. There we go. We've got our difference vector now. What we're going to do next is we're going to construct a quaternion from this difference vector. And the way we can do that is just by typing quaternion look rotation equals quaternion dot look rotation. Alright, we have two overloaded functions right here. We are going to use the second one and provide it our own upward vector. So let's go ahead and tell it that the forward vector, in other words, the forward vector is the direction we should be looking in, is going to be the difference vector we just constructed on line 21. So that's going to be difference vector, comma, okay, what is our upward vector? Our upward vector is vector 3 dot up. That is basically just the upward y-axis. In other words, we're saying that the up we want is the up that is in our world. In other words, if you are just standing on that concrete and you look up, that's the up that we are using right here. And as it says here, it's also shorthand for writing vector 3010. Sometimes there's these little shortcuts you can use to make your code writing faster. We got our difference vector, constructed a look rotation from our difference vector. Now what we're going to do is we're going to tell our rotation to change towards the look rotation. We're going to do that by typing transform.rotation equals and we're going to say quaternion dot rotate towards. You can think of this as being an analog to, or basically the same thing as what's happening with line 19, our lerp, except instead of using a percentage over here, we're going to be just telling it how many degrees can it change. So let's go ahead and say rotate towards, and the first thing is our starting rotation. We're going to just say transform.rotation, and then the quaternion that we're rotating towards is the one that we just constructed on line 23. It's the direction we want to look in. The first quaternion is the direction we are looking in. The second quaternion is the rotation we want to look towards. So we'll say quaternion look rotation. There we go. And here we're going to be saying 10F. We're putting in a float. We're saying that the maximum degree delta we want to change is 10 degrees. This is going to be broken up into pieces among the different axes of rotation. We can rotate around the y-axis, around the x-axis, around the z-axis. All right. So we have the transform.rotation equals this. So this is pretty good, and I think we should give it a try now. All right, let's hit the run button, and hopefully we're going to get a nice rotation. Oh, isn't that wonderful? Look at that. It just nicely turns the camera. Just angles the camera nicely, right? Isn't that nice? Nice, and feels almost buttery smooth, and that's what you want, right? That's what you want in a camera system. A nice little buttery smooth transition system. All right. So, what about the turning? You guys saw at the beginning of the video that we were adding some turning systems in with Q and E as input. Well, let's pop back into our script right here. And if I show you my original one, we had a private float. This is not visible in the editor, but it doesn't need to be visible in the editor because basically we're going to start with a rotation of 0, and really it's just going to get increased and decreased by lines 26 and 31. All right, so let's go ahead and set up our Y rotation, our rotation around the Y-axis basically. And we'll say here private float Y rotation. If I don't write anything, by default it will be set to 0F. It initializes itself. That's a nice little feature. But if you wanted to, for example, change the default rotation, we actually say something like 90F, and it will start at a different camera angle when we actually run the game. So our next step is to actually check for input. So let's go ahead and add in some code over here. We'll say if input.getKey. And at this point, I'd like to actually talk about the difference between getKey and getKey down. All right, just a little piece of advice and information. GetKey checks if you have the key pressed. GetKey down checks if you have if press the key in an individual frame. It doesn't know if you're holding it. It just checks if you have only pressed it down. Get key down is basically kind of like the jump button in our game. You're not really checking the holding of the button like you would for directions or directional movement. All right, so we're going to put our parentheses down over here, and we're going to put in key code dot. Let's see. So let's do Q rotation first. All right. Okay. So if you guys remember your clocks, you can remember that one of them is positive rotation, the other is negative rotation. quiz question in your heads right now. Can you remember if clockwise is positive or negative? Well, time's up. So clockwise motion, or Q, is actually positive rotation, right? Well, is it? Let me double check that. Ooh, is it actually? Yes, it is. It is positive rotation. Just to double check that. Yes. So we're going to take our Y rotation plus equals. What does this mean? What does this plus equals do? This plus equals says take the Y rotation and add to it whatever's on the right side. So we're basically saying, okay, if it's 90, we're going to increase it by a certain amount. For now, let's see. What did I use for this? I used rotation transition speed. Okay, well, let's assign it some initial value. Let's do 0.5f. And times it by time.delta time. 0.5f becomes a velocity in that case. It's in a rotational velocity. Delta time. And if input.getKey code.e. Alright, well, if Q is positive, then E to undo Q would have to be negative. Y rotation minus equal 0.5f times time.delta time. Okay, well, we've got this fancy pants Y rotation variable now. How can we use it? Well, let's see if you guys remember your trigonometry. What we're going to do is we're actually going to modify this offset vector. I used a value of 8f for the x, or was it the z-axis? It's the z-axis displacement. I'm saying, okay, we're going to be 8 away on the z-axis and 0 away on the x-axis. But to get rotation going, you got to remember your sines and cosines. What we're going to do is we're going to say offset vector equals new vector 3. All right, this is the constructor for a vector 3, and we're basically just replacing what offset vector was with something new. We're doing a replacement here. The x value, we want it to be the sine of the y rotation. To do that, we can just type mathf.sine, and this is a function, so we'll throw down a parentheses, and inside of here we're going to put in y rotation. Then we're going to throw in, well, we want to keep our y offset vector. Basically, however much high or low we are, that's not something that should be changing. So we're just going to use the original offset vector for y. So offset vector dot y. Lastly, should be pretty clear at this point, we need the cosine, right? So mathf.cosine, and we're going to put in the cosine of the y rotation again. Okay, now if we use just the sine and cosine by itself, the problem is that the amplitude is going to be 1. It's going to be way too close to the cube, in other words. We're going to multiply it by 8f to achieve that 8f displacement that I had earlier. So now these are sinusoidal functions with an amplitude of 8. You can, if you want, make a public variable, a public float, and you could actually manually set these two yourself. And it would be an experiment worth considering. Alright, we have 0.5 times time.delta time. We've changed our offset vector, and then we use our offset vector to determine where we should lerp our position to. So I think we're about ready to test this out. Let's give this a little run and see how it looks. Alright, so there's our 90F, and let's see what happens if I move it around a little bit. So the camera still follows properly. Now let's see what happens if I press E. If I E, I rotate to the right. Does the camera still work properly? It does. It does. Perfect. So, what if I press Q? Does it still work properly? Let's move over here to this side. Okay. And we can click on our red cube, and we can move around here a little bit. Look at what happens, though, when we actually... Interesting little behavior. When you actually go underneath it, it has a little bit of a visual glitch. This is something that we probably need to do some optimization on to make it look the way we want. it may just need or require a faster positioned lerp. Because if the red cube's moving really fast, then it might cause some quick rotational glitches like that. And we want to keep that to a minimum. So you may want to increase the rotational lerp speed, or the positional lerp speed, so we don't get those rotational lerp glitches. Not very nice looking. Alright, let's go back to the editor now, and let's see if we can do a little bit more. Now we can start throwing in these parameters. Let's say I don't like 0.5f. I don't like that. It's too slow. So I'm just going to go over here, and I'm going to make a new float, public float rotation transition speed, and set it equal to 1.0f. Alright, let's double that, and then I can just throw these in over here. Alright, saved. Let's pop back into Unity, and let's look at the main camera now. Let's go back to the main camera, pull up the inspector, and over here on the camera controller script, I've got the offset transition speed 2, rotation transition speed 1. Let's amp this up to 4, and let's try this at 1.5. Alright, give this a little run. Let's see if it works the way we want it to. Alright, that was a much quicker lerp. Let's actually see what happens when we move it around a little bit. Not too bad. Okay, what about when I do some... Ooh, very nice. This is my Q and my E rotation. Now I'm using 1.5F. It's working very nicely. Very nicely indeed. Alright. Well, that's about it for this video. I want to keep making this content. So, please like and subscribe this video if you would like to see more. I'm looking at doing some shader work here as well. I'd like to ideally hit on a lot of the major topics of game development. So give me a like and subscribe so I can keep doing this for you guys.